All right, so here is section 3.2, okay? And as discussed in previous sections, what we're going to start looking at now is instead of only doing things in one direction, so only in the x direction or only in the y direction, we're now going to start dealing with things that are happening in both directions at the same time, right? Because a lot of times in life, things aren't only happening in one direction, they're happening in multiple directions. So what makes this tricky is now you have to start taking into account two different directions. So what I recommend is I say always start an X column and a Y column. That way you can keep all of your stuff separate, right? You can keep all your X displacements and accelerations and velocities and all your Y stuff, all that stuff separate, right? Because we have accelerations and velocities and displacements for both the x's and the y's. Really, the only thing that translates between the two of them that's the same is going to be time, okay? Notice the kinematic equations are the same. It's just that we switch the x's and the y's. So everything's still, the same from previous sections, except now we're going to bring it all together, okay? So right here they say it is important to realize that the x part of the motion occurs exactly as it would if the y part did not occur at all. Similarly, the y part of the motion occurs exactly as it would if the x part of the motion does not exist. In other words, the x and the y motions are independent of each other. Again, let me stress that. The x's and the y's occur completely independently. So x would still do whatever even if y wasn't there, and y would still do whatever even if x wasn't there, okay? So they're completely independent of each other. Everything that we have learned in Chapter 2 about kinematics in one dimension will now be applied separately to each of the two directions. In so doing, we will be able to describe the x and y variables separately and then bring these descriptions together to understand the two-dimensional picture, okay? So, in example 1, it says in figure 3.5, the directions to the right and upward are positive directions. In the x direction, the spacecraft has an initial velocity component of v0x of 22 meters per second and an acceleration component of ax being positive 24 meters per second squared. In the y direction, the analogous quantities of v0y are 14 meters per second and ay is 12 meters per second squared. So in other words, the acceleration in the y direction. Now, oftentimes we say that a sub y in the acceleration in the y direction is negative 9.8 meters per second, but they have changed that here. Notice that it's 12 meters per second squared. So our usual assumption that we would have of negative 9.8, you wouldn't want to use that because they have specified otherwise. At the time t equals 7 seconds, find the x and y components of the spacecraft's displacement. So what we're looking for is we are looking for the x and the y displacement, okay? The x and the y displacement. So what we want to do is, just like I said, okay, you would want to start an x column and a y column. Because what we're going to do is we're going to list out everything that we know about both my x's and my y's. So here you go. You got v0x. In other words, your initial velocity in the x direction is 22 meters per second. We also know that my ax is 24 meters per second squared. In the y direction, we have v0y to be 14 meters per second. And again, we don't want to assume this one in this case because we're given ay, and this is going to be 12 meters per second squared, right? And what we're actually looking for is we're looking for the x displacement and for the y displacement. That's what we're looking for. So when you go back, right, when you go back and you look at your kinematic equations, you're going to look for something that deals with the x, right, the x displacement, but also takes into account things like v0x and ax, right? You're going to look for things, because remember, these are completely separate. Now do the same thing and look for an equation that deals with the v0y and the ay and that can find your overall displacement, right? So when you go look at your kinematic equations, right, one of the best fitting, and not saying that you couldn't use perhaps another one, but one of the ones, because I didn't look at all the equations, but I do know that the one that is going to fit is listed right here, right? They show us, look, they say x equals v0t plus 1/2 ax t squared. Now, remember, this is v0x, right? Because we're talking about the x direction, okay? So all we got to do now is we plug in, well, we have v0x. There it is, 22. We already have our time, which is going to be, oh, one other thing that we could list in both columns, right, would be t equals 7 seconds. So we could put that in both columns, right? 7 seconds. Okay, so there you go. You got 7 seconds in both columns. So you can use that to your advantage. So there you go. We got time. We were given AX and we already had T. So when you plug all that in, you come up with 740 meters in the positive direction. In other words, it is moving in the X direction to the right. Okay. Well, obviously, if this worked for the X, right, this equation is going to work the same for the y, because we're given the same information. It's just now we got to go ahead and we got to switch all of our variables to be y. So that's what we're going to do. Y equals v0yt plus 1/2 ayt squared. And that's all they do. Look, we have all this information. We were given 14 meters per second, 7 seconds, 12 meters per second squared is my ay, times 7 times the 1/2, and we come out with a positive 390 meters. Okay, so that's that equation. Again, nothing has changed from before. It's just a little bit more tricky now because you've got multiple directions going at one time, so you got to remember to keep them straight. Next example says the velocity of a spacecraft. This example also deals with the spacecraft in figure 3.5. As in example 1, the x component of the craft's initial velocity and acceleration are v0x, 22 meters per second, and ax, 24 meters per second squared, respectively. A corresponding y component of v0y is 14 meters per second, and an ay is 12 meters per second squared. At time t equals 7 seconds, find the spacecraft's final velocity, magnitude, and direction. Now, this one is tricky because notice they say final velocity. Now, this means the overall velocity. So what you need to do is you need to take into account Vx and Vy, right? Vx and Vy, and basically come out with the new overall velocity. So it's essentially like you're going to find Vx and Vy, and then you're going to find the hypotenuse, and that is the final velocity, that hypotenuse, okay? So just like we did before, right? We would start with, by labeling everything that we have. So on your x, you have V0x to be 22 meters per second, and you would do the same with the y column, V0y, and you would come up with 14 meters per second. And basically what you're going to do is you're going to jot down all the stuff that you know, same as we did before, right? We had time equals. Now this time, we're not searching for displacement, right? We're not searching for displacement. We're trying to find the final velocity in the x direction and the final velocity in the y direction, because once I have those final velocities for x and y, I can determine this overall final velocity that they're looking for. In other words, that hypotenuse that we talked about before. So what they're going to do in this problem is they're going to go back and they're going to examine all of their equations, and they're going to come up with an equation that works. Well, one of the equations that would work, especially to find my Vx, right, would be my final velocity. So I'm looking at V in my x direction is equal to V0x plus AXT, right? Well, I know that my V0x is 22 plus 24 times 7. And that's going to give me my Vx, okay? That's going to give me my Vx, which comes out to be I come up with 190 is what I came up with. All right, so that's your Vx, which you're going to need here in a couple minutes. Vy, I believe the same thing will work because, look, we have the same information. So Vy, in other words, my final velocity in my y direction, would equal V0y plus AXT, right? So again, Vy is equal to, in this case, let's see, V0y, we had 14 plus, we had 12 times 7 in this case. And if I do my math correct, I come up with a value of 98 on this one, all right? 98 in that one. So what this tells me now is it tells me that my rocket is moving this way, 190 meters per second, and it's going this way, essentially like this, 98 meters per second, which is basically going to give it a trajectory like this, and this is going to be my overall V. Now, really, you can transpose this up to here or move this one over to here to create your right triangle, and it doesn't matter which way you do it, but we'll go this way. We know that this is going to be 190, and we know that this is going to be 98, which now gives me, in order to find my V, is simply going to be the Pythagorean theorem. So it's going to be the square root of 98 squared plus 190 squared, and that should be my final velocity. Let's see here. So if we do this, we're talking about taking the, let's clear this out. We're going to take the square root of 98 squared plus 190, let's see here, 190 squared. And we need to square that. And, no, we did it too many times. Let's come back to here. Let's get rid of this one. Right, let's see here. Now, does it come out the way that we need it to? No, I missed a parenthesis. Let's try that. And now it looks like we're okay, right? So now it looks like we come up with 213 meters per second, right? 213 meters per second is what I come up with. Really, we could round that up to 214, right? So back here, we could say this is 214. So this is 214 meters per second. So your overall velocity, that final velocity that they speak of, right? The final velocity that they speak of would be 214 meters per second, or 213.7. I rounded up a little bit. The book actually gets 210, I believe. Again, it just has to do with how many decimal points you carry. Now, though, you want to be careful because even though this is 214, right, and that's one of the answers that we were looking for, it said magnitude and direction. In other words, you need to find this theta, magnitude and direction. So you guys remember this from before. You could do the inverse of multiple things. You could do inverse tangent, inverse secant, or inverse tangent, inverse sine, inverse cosine. Any of the above would work. And I believe that they're going to do maybe an inverse tangent here in the example. They do inverse tangent. So if we were to do inverse tangent, basically what you would do, because you had this to be 214, I believe this one was 98 and this was 190 from what I had before. And again, I'm going off memory, so I apologize if I messed those up a little bit. Just put in the correct numbers that should be in there. And then you would just do the inverse tangent of opposite over adjacent, right? Because tangent, opposite over adjacent. So if this is correct, and again, I'm not exactly sure from before, but I think it was 98 and 190. The opposite would be 98 divided by 190. Do the inverse tangent, and you should come up with somewhere in the neighborhood of about 27 degrees. So that's how you do problems like that. And again, the section isn't anything different than the stuff that we've been doing. It's just more complicated now because now you got two things going on. You got X direction stuff and Y direction stuff, and you just got to keep them all separated. And if you're able to keep them all separated, then you can just find each of the things that you need, bring them together, and find the overall of what you're looking for.